All right, folks, here we go. This is example 3 for the normal approximation to the binomial distribution. Again, I would suggest you familiarize yourself with the questions before you start watching the video. So, we have sampled 80 US drivers, that's our N, and each one of those 80 is either going to text while they drive or not. All right, so that's the so-called success failure. All right. So, we are told that 1 out of every 5 US drivers texts while driving, and 1 divided by 5 is 0.2. I would always suggest if the fraction becomes a nice pretty decimal to take advantage of that. Therefore, the Q would be 4 out of every 5, 0.8, and there we go, we've got our binomial. Now, when you survey 80 people, you could have anywhere from 0 to all 80 of them who admit to texting while driving. And that's considered success here. I am not calling you a success if you text while driving. As a matter of fact, please don't text while driving. Put your phone in the console. All right, so there's your fatherly advice. Fatherly advice. Who are you? But anyway, here's the deal. So you look at this, and we're doing part A here now, and it says, what's the probability that of those 80 drivers, more than 15 of them text while driving? So in this list of numbers from 0 to 80, wouldn't that be all the x's that are greater than 15? More than 15, right? Now, again, I want you to see the overview here. So wouldn't that be, let's 1, 2, 3, 4, dot, 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 14, 15, 16, dot, 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 78, 79, 80, 0 to 80, right? More than 15 would be all these numbers from 16 on up, wouldn't it? All right, and that would be, if you want to get the exact answer, you could do that formula for all the numbers from 16 to 80. Yeah, woohoo! That formula we did on assignment 15. All right, now, if you were going to do the formula approach, that would work, but let's just talk about it real quick. The faster way, though, would be to do the formula for the numbers from 0 to 15. That's less work. Add those up and take it away from 1. But either way, it's a lot of work. If you're going to do it, the assignment 15 binomial formula approach. So the mathematician would look at this and say, yeah, that'd be a lot of fun, but could I maybe use a bell curve as a substitute for this binomial experiment? Would the histogram of this resemble a bell curve? And again, smart mathematicians, so I'm over here, I'm going, can we use a bell curve? That's my little logo for it. Let's investigate whether a bell curve is appropriate here. So we check the two rules, n times p, which in this case would be 80 times 0.2. You go, well, that's 16, that's more than 5, right? Greater than or equal to 5. That's the first thing you check, and you go, check, good. And if it passes the first one, then you check the other one. Now look, if the q is bigger, 0.8, then obviously, but I just check them both. Why not? It's more math, okay? But anyway, the point is that's 64, n times q. That's also more than 5. Yay! So the point is the mathematicians of the world have determined that if you pass those two rules, the histogram of all these probabilities from 0 to 80 would close enough resemble a bell curve, all right? So that's the point. And so the idea now would be, yay! We can use a normal distribution, bell curve, wait, it's not 0, and as a substitute for this. It's going to be off a little bit, that's why it's called approximation, but there you go. All right, so yes, we can do this. I need to make space here, so after we check this, and keep in mind, this has already been checked for every part of the question in example 3. We've established bell curve is indeed appropriate. We've checked these rules. I have to erase this to make room, but it would apply to every other part to this example, wouldn't it? Parts B, C, D, and so on. All right, what else is going to apply? The mean and the standard deviation. So the mean, n times p, which in this case is 80 times 0.2, which is 16, all right? Okay, so that'll be the mean, and that'll apply to every part of this example, won't it? They're all going to be a bell curve as established in part 1, and they're all going to have a mean of 16. All right, standard deviation would be the square root of 80 times 0.2 times 0.8. Now, I believe this is going to be some crazy decimal, all right? So we're going to have to keep that to the best of our abilities. 80 times 0.2 times 0.8. 80 times 0.2 times 0.8. Sorry, I get nervous in front of big audiences here. The entire world is watching this, aren't they? So 80 times 0.2 times 0.8, 80 times 0.2 times 0.8, and then the square root of that, and I'm getting 3.577708764. I'm really nervous not being able to hear you guys tell me when I mess up, because you're very good about gently correcting me when I mess up. And if I did wrong there, sorry, I'm not hearing you very well. But I think that's right. It's important to get every one of these numbers correct, obviously. All right, now, I think the biggest issue in this series of examples, and we're going to do parts A and B side by side to see that difference, is that step correct for continuity, all right, by 0.5. So, this is the visual I've been using for years and years and years, is a number line to represent x. 15 is the number that we're talking about. Now when it says greater than 15, we're not including 15 in that picture. So in algebra you learned that the visual was to put an open circle on the 15, a dot, a hollow, and then go above. Okay? I think this visual works very well. Obviously other people in the world might have other things that they would suggest you do, but to me that's a picture of greater than 15, more than 15. And it all goes back to the wording in the question, more than 15, more than 15. That does not include 15. This is a picture of does not include 15, more than, in my opinion. All right, so back to the correction for continuity by 0.5. What direction should we go if we don't care about keeping 15 in the picture? I hope y'all would agree we should go above it and run away from it. Wouldn't that leave 15 in our rearview mirror? Goodbye, 15. I'm going above you and running away. I don't know, that seems to have worked for a lot of people before. Again, every time we do an example, you'll get better and better at this. But this is probably the most critical step in the process, is to remember to do this and to do it properly. So the point is, this transitions to, see, I drew this bell curve down here because we got to make this adjustment before we do the bell curve. Wouldn't that be the probability that x is greater than 15.5? All right, there you go. So we went up, we went above it, ran away from it. Goodbye, 15. The problem said more than. We don't want to keep 15 in the discussion. So at this point in time, we actually have, and 15.5 would be below the mean, wouldn't it? And here we go. So at this juncture, everybody's hopefully going, well, this is just assignment 17 right now. I'll just go solve it as a normal distribution like we did back then. In other words, step 4 in the notes. So you go back and you do that. And see how things just kind of keep working backwards. And so at that point, we gave you a question that became this basically on assignment 17, those applications of the normal distribution. And so what we did, if you recall, was we drew a standard normal bell curve. We put a number below the mean, shaded the same region, and we just need to figure out what z-score corresponded to that particular value of x. And here's our interpreter. Hello, I changed x's into z's so that you can go to the table. Right? Okay, so there's our deal. So then the x changes into z. We standardize that score. 15.5 minus the mean, which is 16, all over the standard deviation, which unfortunately is this crazy number I'm standing in front of that we found earlier, 3.577708764. You could probably drop some of those digits and get away with it, but I would suggest not. So let's keep every one of them there. And so let's see, 15.5 minus 16 would be negative 0.5 divided by that crazy standard deviation. Z-scores get rounded for the purposes of our table to 2 decimal places, negative 0.14, and that would be the Z-score here. There you go. All right. So now what? Oh, now we can go to that table, can't we? So the point again would be that once we've standardized that score like we did on assignment 17, this is now assignment 16. So we now go back and we use the table to finish out the question, don't we? So here we go. Do you have to do it every time? Probably not. Table time. All right, so 0.14, middle sliver of 0.0557. It obviously is very important to be able to read that table there. So what did I just say? 0.0557. 0.0557 from the table. Now remember, that's this right here, isn't it? And I hope everybody would agree that according to the appearance of this table, in this example, we need to add that upper half of the bell curve to get this entire probability, don't we? So we add those two together, which I'll do up here. So we'll take that middle sliver that the table gave us, 0.0557, add the upper half of the bell curve, and it looks like 0.5557 should be the final answer here. You will find in your notes, in your examples, I guess I should say, whatever you want to call it, that I did indeed type up an answer slide for these examples, and I did indeed get 0.5557 there. So, one more time, what would that be? If you calculated every probability for all those numbers that are greater than 15, all the way from 16 to 80, using that formula that we did on assignment 15, you should get a number pretty close to that, but you obviously got it in a much faster way. So I would think, I'm going to pair these together, and I did this on purpose. Let's transition that into part B, all right? Because these have very similar wording, but just by changing the wording just a little bit, you can tell what's going to happen here. So let's build off of this. Now we're going to do part B. We've already established the mean, the standard deviation, the fact that it's okay to use a bell curve here. But when we go to part B, the question now says, what's the probability that at least 15? So what's different about that? Instead of more than 15, it says at least 15. Doesn't that mean greater than or equal to 15? At least, that's 15 or more. So what happens back here is now we go, okay, 15, now we're going to include you in the party, aren't we? Doesn't that increase our range of numbers by one more, 15. You're in the party now, 15. See how that changes it just a little? And that very small change in wording has a huge impact on how we reason out the rest of the question. So now we're talking about greater than or equal to 15 as opposed to just greater than 15. What does that impact the most? Correcting for continuity. That's the one, and that's what I'm practicing here. So, what happened here? See, I'm just kind of building off of the previous work. Hit the pause button whenever you need to and catch up to me. At least 15 means 15, you're in the party now. Notice I solidified that, right? 15 is now included in the discussion. And I would hope you would agree then that when we correct for continuity, this time we'd want to go below the 15 by 0.5 and run through it so as to keep 15 in the discussion. So I'm being lazy here. I did this on purpose, but shouldn't that be corrected now to 15 minus 0.5, 14.5, which changes this to 14.5. I'm lazy, aren't I? Hey, look, work smarter, not harder. Anyway, so, including 15 in the discussion, we're going to come below it and run through it, 14.5. And when we go and standardize that score, all right, so now we're ready to go back to, oh, okay, assignment 17, assignment 16, right? Standardize that score. this time we're going to do 14.5 minus the mean over the standard deviation. The mean and standard deviation stay the same, right? It's just that x value changed. Again, because of that difference in correcting for continuity. So this time, it looks like, and this is where I'm nervous because one little arithmetic mistake is out there forever. And so, boy, this is exciting watching this, isn't it? I see negative 0.419, which I'm going to call negative 0.42. And so negative 0.42 below the mean, right? Negative 0.42 would be the z-score for this new value of x. Just by changing that one word in the question, it impacts the correction for continuity, which of course impacts everything else. And then we go back to the table, right? And we'll look up, this time we'll look up 0.42. So 0.42 looks like, I hope you remember how to read the table. You've got one in front of you. 0.42 is 0.1628. And so that would be that middle sliver this time. And just like the previous one, you got that middle sliver, you got the upper half of the bell curve. And so 0.1628 plus 0.5, upper half of the bell curve, would give us 0.6628. That would be the final answer here, all right? So I ask you to circle your answers. There's numbers all over the place. If I had more board space, I'd do a better job of putting things where they're easier to follow. I'm doing the best I can with the space that I have. But anyway, looking at the answer slide, whoo, 0.6628, awesome. So to me, those two questions went together because, again, of just that little change in wording. So pay attention very carefully. If it says more than 15, you're not including 15. If it says at least 15, you are. So that's examples 3, part A and B, and let's continue practicing.